Hello. In this brief video, we're going to continue with the types of reactions we were writing before between acids and bases and trying to predict the reaction type that is most likely to occur when we're dealing with a particular acid and base. So once again, this is a pretty important concept because we're going to build on it after the reading week break, and we're going to talk more about something called equilibrium, which has to do with reactions that don't go to 100% completion. They actually go between the reactants and products. They move back and forth between the reactants and products. So just as we started last lecture, I'm going to go over one of the questions we did before, just by way of moving us into the topic at hand. So remember last question that we did together, we were using our acid-base table and trying to pull out or identify the important reactants in a particular mixture that were likely to react. So there was a 5-step method that we were using, and the first step was to list all of the species we had present in a particular reaction mixture, and that's what we have up here. All right, so this is our list of the species present. The second step was then to identify which were the acids and bases in this list, and then to pick the strongest acid and strongest base. Now I'm just going to back up to step 1 for a second, just to remind you that when we deal with high solubility ionic compounds, because there was a question on Wednesday's class about how do we know when to split up the sodium and hydrogen sulfide? Well, if we've got a high solubility ionic compound, and again you can check your data booklet on page 6 to see which ionic compounds are high solubility. If you have a high solubility ionic compound, you split it up, and that's why in this case we wrote the Na and the hydrogen sulfide separately, because in solution in water they are going to break apart into ions. The strong acid, on the other hand, it's not a strong acid, it's the strongest acid that we have in our list. We're going to keep it in its molecular form, and again, the reason we do that, it's not a strong acid, it's the strongest acid that we have in this mixture. It is one of the weak acids. So weak acids we keep in the molecular form. We don't break them apart, we don't ionize them. And of course, in all solutions we have water. So once we've gone through this list, listing all of the species present, identifying the strongest acid, identifying the strongest base, then we write our reaction occurring between the strongest acid we have in our list and the strongest base, remembering that acids want to donate or give away a proton. Bases, on the other hand, this is the base over here, this was the acid. Bases, on the other hand, want to receive a proton. So if we take a look on the product side of the table, we see that after the acid has given away its proton, it becomes HCOO negative over on this side. The base, on the other hand, once it's accepted a proton, becomes H2S. We also, on Wednesday, introduced this idea of an acid-base conjugate pair. So if I take a look at these two, for example, the HS on one side and the H2S on the other, we identified in the forward reaction that HS was accepting a proton. So over on this side in the forward reaction, it's acting as a base. If I look at the reverse reaction, on the other hand, so if I were to look at this reaction going in the opposite direction, starting with the H2S as a reactant, and HCOO negative as the other reactant, so if I'm looking at it going in this direction, this is actually acting as an acid because it's donating, it's giving its proton to HCOO negative, and that's going to become the acid on this side. So this HCOO negative on the product side, if I look at the reverse reaction, it's actually acting as a base. So we defined a conjugate acid base as two species that are virtually identical. They're almost the same. The only difference between them is an H positive. So in this case, we've got HS negative. On the other side, we've got H2S. So the only difference between these two, the H2S and the HS, is a single hydrogen ion. So those two together are called a conjugate acid-base pair. AB just means acid-base, conjugate acid-base pair. And of course there are two of them, because if we look at the acid on the reactant side, and this ion, HCOO negative, which the acid becomes, if I look at the reverse reaction again, the reverse reaction, this is acting as a base. The HCOO negative is acting as a base. Over on this side, a species that looks almost identical to it, the only difference is it's got the extra H added on, is actually acting as an acid. So again, those two together, they're identical, virtually identical. The only difference is one of them has an extra H plus compared to the other. So those two are also called a conjugate acid-base pair. So we have two conjugate acid-base pairs in this acid-base reaction. That will always be the case with acid-base reactions, if we look at them in the forward direction, and if we can look at them in the reverse direction. Now don't forget, if we've got a strong acid involved in this reaction at all, we're not going to have this double-headed arrow. It's only going to go in the forward direction. Similarly, if there's a strong base involved, we're not going to have that double-headed arrow. So if we scroll back, we had an example early on where we did have a strong acid. There we go. This one, and it even tells us in the question, right, that it's a quantitative reaction. Quantitative means it's 100%. It goes 100% towards the products. And the reason for that is this reaction involved nitric acid, HNO3, and if we look at our table of acids, we'll notice that nitric acid is a strong acid. It's above the gray line. So in my reaction, I didn't write nitric acid. I replaced it with H3O positive. And that's always going to be the case when you've got a strong acid. Okay, above the gray line, a strong acid, you're going to replace it with H3O positive. And that means that we're going to have a 100% reaction, and you'll notice there's only the single-headed arrow. That means all the reactants go to form products. So we want to take a look at a couple more examples, at least one more. Let's try one more, and just to make sure that we can use this 5-step process to predict the predominant reaction. Again, we're only looking at the reaction that occurs between the strongest acid and the strongest base that are present. So let's take a look at this example now. Predict the predominant reaction when a vinegar solution, so I need to identify what my reactants are. Vinegar solution is going to be reacting with a household bleach solution. Okay, so I'll just pause it here, and you can work on that, and I'll post a solution right after.